This is the first screencast for our Unit 9 on exponential equations and functions. Before we can solve exponential equations, we want to do a thorough review of the laws of exponents. All of these laws of exponents you should have seen already in integrated algebra, but we do need to do that thorough review. So let's get started. We'll start off by looking at what happens when we're trying to add or subtract terms that are not alike. If you have terms that are not alike, you're not allowed to add or subtract them. And how do you determine if these are like terms or not? Well, you cover up coefficients. And I'm going to put these yellow spots in front of the x to the fifth and in front of the x to the fourth. They would be representing our coefficients. When you look at everything else that's left over, they have to be exactly the same. Here I'm seeing an x to the fifth, and here I'm seeing an x to the fourth, so they are not exactly the same, so that would tell me right there that I'm not allowed to combine those two terms. When it comes to dealing with multiplication and division, all the rules change, and that's true whether we're working with algebraic terms, whether we're working with complex numbers with i's in them, whether we're working with radicals. We cannot add or subtract. We can't combine things that aren't alike, but we can always multiply and divide things even if they're not alike. So we'll look at our two examples here. First example being x to the fifth times x to the fourth. Second example being x to the fifth divided by x to the fourth. Now, I'm going to guess that most of you would be tempted to go ahead and write x to the ninth as this answer, and you would be correct. And this one is x to the first power, which we're going to write as a plain old x, and that's also correct. But the point I want to make when you're looking at this is that whenever you apply these rules, the base has to be the same. Those had to be both x's, otherwise we couldn't apply those rules of exponents. And in the answer, we'll keep that base the same as what it started off as. When we're dividing, we have a base of x on top, we have a base of x on the bottom. That's what allows us to divide these two and to just subtract those exponents. 5 minus 4 is equal to 1. Notice that in our answer, after we subtract, the base is also the same. So just take a note there that these bases have not changed. The bases don't change, and it doesn't change when you're working with numbers. Still, the bases won't change. So look at a couple of more examples down here. You have your basic multiplication, you have your basic division. We have some shortcuts we can do. So let's look at what the shortcuts look like. First of all, there's this shortcut that says when you're taking something and raising it to the fourth power, first of all, I'll write it out the long way. I don't want you to do this every time. You'll never have time to finish a test if you're going to be writing this out all the time. It's x to the fifth times x to the fifth times x to the fifth times x to the fifth. And when you see that, you have 1, 2, 3, 4 bases that are exactly the same, and I'm multiplying. That's what the back-to-back parentheses mean. So my answer here still has an x in its base. Remember, just like up top here, we have all the same base, so that allows us to use laws of exponents, and we'll have that same base in our answer. When we multiplied up top here, we said, well, we know that we're just supposed to add the exponents. 5 plus 4 is 9. That gives us an answer. So now down the bottom here, we've got 5 plus 5 plus 5 plus 5, and you add those four numbers together, you get 20. Well, the result is that the multiplication right here, 5 times 4, giving me 20, would really just be a shortcut for adding the 5 4 separate times. And in fact, multiplication is a shortcut for repeated addition. So we can just go straight from this expression to this answer. You do not have to write all this out, but I did want to show you where it comes from and why that rule works for us. Okay, one more thing down the bottom of this page here. And that's going to be a shortcut we can take when we're working with fractions. Anytime you're working with fractions, when you're raising that fraction to a power, in this case we're raising the fraction to the fifth power, I can say the equivalent of that is the numerator of the fraction raised to the fifth power divided by the denominator of the fraction raised to the fifth power. And this little device works both ways. You can go in the forwards and you can go backwards with this thing. Either direction will work fine here. So if you start with two things on top and the bottom raise the same power, you can put them in parentheses and raise it to all one power. So just keep in mind, sometimes you're going one way, sometimes you're going the other way. It depends what the problem calls for. Everything I've shown you on this page is just very basic rules. When you do the homework sheet for day one, you're going to notice that there's a lot of things that you'll have to build into each problem. But all of those things you build into each problem come from the basic rules that we're reviewing now. Moving on to the second page here. Anything to the 0 power is equal to 1. You've heard that before. You've used that before. Let's talk about some particulars. First of all, let's look at this little example. It'll say why this works for us the way it does. If I have x to the 5th over x to the 5th, and I apply that rule that says I can subtract exponents, we know the answer is 1. We know that everything's going to cancel out here. But let's look at the exponent rule. X to the 5 minus 5 is x to the 0. And so we know x to the 0 is 1. So this x to the 0 equals 1, which we saw in our rule here, is proven when we divide by the subtraction of the exponents showing x to the 5th over x to the 5th. More. No negative exponents are allowed in answers. Now when I say that, I'm talking about simplified answers. You do have one section on the homework sheet in which you are supposed to leave your negative exponents in the problem, but those are not simplified answers. Those are specifically asking you to provide answers that aren't simplified. Generally speaking, whenever you give me an answer on an answer line, you will not have any exponents in that answer, because generally speaking we give simplified answers. So the way to get rid of negative exponents is to move them. A lot of people think reciprocals when they see negative exponents, but they're not reciprocals. Only in a few select cases are they reciprocals. We're going to deal with negative exponents by moving instead. So let's take a look at this problem here. In this problem here, we have some things that have negative exponents on them. We have other things that don't. So the only things we're going to move is the things that have negative exponents on them. This a to the minus m will have to move to the bottom. And when it moves to the bottom, the negative's gone. It's now a positive m. This b to the 3rd is going nowhere. There's no reason to move it anywhere. It doesn't have a negative exponent. I'm going to leave it up top. This y to the minus 2 does have a negative exponent, so I'll move that y to the minus 2 up top. When I do, it becomes y to the positive 2. And here's my answer, a simplified answer with no negative exponents. That's not a reciprocal of what we started with. On the second example down here, I've got k to the minus 3. Well, we know we've got to take care of a minus 3. We know we've got to move it somewhere, but it doesn't look like there's any place to move it to. Well, that's easy enough to take care of. If I need a place to move it to, I'll just create a place to move it to. Just add a denominator into the problem, and now it'll give you some place that you can move that k to the minus 3 to. It was on top. We're going to move it to the bottom of the fraction. When we do, it becomes k to the 3rd. This 1 stays on top of the fraction up here, and so there is my simplified answer, 1 over k to the 3rd. And I think that's it for the problems down here. Let me see if there are any more. Oh, there is one more. Okay. So basically we're going to move. So let me show you the move in this one, and then after I show you the move, I'll show you a shortcut. First order of business, we're going to rewrite this. We're going to apply that minus 4 to the c on top. We're going to apply that minus 4 to the g on the bottom. And now we'll take the c to the minus 4 that's on the top. We'll move that to the bottom of the fraction, becomes a positive 4. We'll take the g to the minus 4 that was on the bottom and we'll move it to the top of the fraction. It becomes a positive 4. My answer here is g to the 4th over c to the 4th, and that is a correct answer as it stands, but we could also put that together into one fraction raised to the 4th power, the g on top and the c on the bottom. So this was a correct simplified answer. This is a correct simplified answer. If you take a look at what happened in between though, look at the start and look at the finish and see everything that happened in between, this gives rise to another shortcut rule we could use. If you have a fraction with a negative exponent outside of it, you can simply flip that fraction over. This is something you would take the reciprocal of, and then that just taking the reciprocal of this fraction would give you a positive exponent outside. Okay, now none of this should be new to you. You actually tested on all this material in the integrated algebra course, so this has all been review at this point. Okay, so let's move on. Let's look at some problems, some important differences between problems. Rules for simplifying. Again, if the problems are problems that you have to simplify, you are not allowed to have any negative exponents in the answer. You are not allowed to have any zero exponents in the answer. We'll take anything that's raised to 0 power, turn it into a 1. And we just like we don't write coefficients of 1, you wouldn't write 1x as an answer, you'd leave that 1 invisible. You also don't write exponents of 1 in your answer. And still we don't write denominators of 1. So when you clean up this, if you have coefficients or exponents or denominators of 1, a cleanup answer would simply be just the x all by itself. Okay, parentheses are a big trouble spot for a lot of people when working with exponents, so I want to show you an example. I want to show you 4 examples, and you'll notice that these 4 examples all look very similar. The only difference between them, for the most part, is where I've placed the parentheses. And you'll see, because of where I place the parentheses, that I'm going to get 4 different answers for these problems. The question is, what do those powers apply to? Well, this 2 out here applies to everything that's inside of the parentheses, but that blue 2 has nothing to do with that coefficient of a -2. Move on to the second problem. This 2 outside the parentheses applies to everything that's inside the parentheses, but it has nothing to do with that minus sign, so the minus sign will just be a bring down. On problem number 3, this blue exponent of 2 applies to, oh, it turns out it applies to everything else in the problem because everything else in the problem is inside the parentheses. And then the last 2 over here, well, things changed a little bit. This 2 applies only to the x to the 5th because that's what's inside the parentheses. Everything else is going to be a bring down. So let's go back and let's do what let's bring down what we have to bring down, and we'll take care of the exponents of 2. The -2 comes down. This is going to become x to the 10th because 5 times 2 is 10. This becomes y to the 6th because 3 times 2 is 6, and that's your simplified answer. In problem number 2, bring down the minus sign. 2 squared is 4. X to the 5th times 2, 5 times 2 gives me x to the 10th. Y to the 3rd raised to the 2nd power gives me y to the 6th. Not bringing anything down here, we actually have to square everything that's in green. Square the minus sign, you'll get a plus. Square a 2, you'll get a 4. Square the x to the 5th, you get x to the 10th. Square the y to the 3rd, you get y to the 6th. And we don't leave pluses in front of numbers as a matter of simplifying. We'll just make sure we get rid of that plus at the end of the problem. The last one, we do bring down the -2. We are going to square just the x to the 5th to give us x to the 10th, and we'll bring down the y to the 3rd. And look at those 4 red answers, and that ought to convince you that the location of those parentheses really is something that's very important, and you really need to pay attention to that. It says monomials versus polynomials. Keep in mind that these are all monomials, these 4 problems. If we were working with a polynomial problem, we've done that already this year. When you see a binomial or a trinomial or anything else inside the parentheses, well, you don't use these rules of exponents. If that's the case, you always write out twice or write out 3 times or however many times you see in that exponent. Write it out and FOIL or distribute until you've completed the problem. Now, if none of this was news to you and you feel like you've got a good handle and you recall a lot from freshman year as far as the laws of exponents, you can stop the video here, but I will do one more slide with some examples on it if you want to watch the examples. In this case, raising everything to the 3rd power, 2 to the 3rd gives me an 8. This leaves me with a y to the 12th. That's my simplified answer. In this problem here, notice that we do have the same bases. When I have the same bases and I'm multiplying, well, my laws of exponents, as we already talked about, tell me to keep the base the same. Now, this negative sign was not involved with 6. I can just bring that negative sign down. I have a negative number times a positive number. My answer will be negative. And let's take care of the exponent on the 2's. 6 plus 2 gives me an 8. It's not exactly a simplified answer, but I could pick up my calculator and ask my calculator what 2 to the 8th is, and that would give me the final number there. On this one right here, we'll take care of the exponents one at a time. We've got different things in the parentheses. all of this green is being raised to the fourth power. When I raise a negative to the fourth power, it becomes positive. Remember, pairs make positives. If you're raising to an even power, a negative number will become a positive number. 2 to the fourth is going to be 16, and x to the first being raised to the fourth power is x to the fourth. So that's the result of my first parentheses in front of the multiplication dot. Let's move on to the second parentheses. In the second parentheses, I'm raising all of that yellow to the second power. 2 squared is going to turn into a 4. And x to the third being raised to the second power turns into x to the sixth. So I've got this little multiplication problem now. 16 times 4 is 64. X to the fourth times x to the sixth, x to the 10th. Circle that answer. It's a simplified answer. We're good. Okay, this one here, we're raising everything in these parentheses to the fifth power, and then we'll multiply by b. So I'll rewrite it first, and you don't have to do this if you're okay with just jumping to a simplified problem for the fraction here. What I'm going to do is, I didn't want to rewrite it that way. Let me erase that. I want to rewrite it as immediately bringing that 5 down to the top and down to the bottom. So 2a to the third to the fifth power over a squared to the fifth power, just using that rule that says that I can split the fraction up by putting the 5 on the top and the bottom. And I know eventually I'm going to multiply by b, so I think at this point I'm just going to bring the b into the top of the fraction. In this first part, raise 2 to the fifth power, that's going to give me 32. The a's will be turned into a to the 15th power. I'll bring the b along. On the bottom, I've got 2 times 5, so that'll give me a to the 10th. And the last thing I want to do is I want to reduce if I can. And we have that law of exponents that says we subtract when we're dividing as long as the base is the same. So this will leave me with a 32, a to the 5th, b, and that would be my solution for that problem. Couple of examples on the homework that you are trying to figure out what the variable is. I think this top one is fairly obvious. 3 squared equals 3 to the x. Well, the only number x could be here would be 2. It's the only thing that will give you a true statement. So x is equal to 2 is my answer here. This one, well, this one's a little bit trickier. I'm going to change that 8 into the same base as I have on the other side. 8 is 2 to the third. I'll bring down that 3 that I had there to start with. So I just changed the 8 to 2 to the third. And now if I simplify the left-hand side becomes 2 to the 9th. It says 2 to the 9th equals 2 to the x, and that means that the only number x can be is a 9. We'll look at 2 final examples. This expression 5 to the b plus 1 is equal to x. 5 to the b is equal to y. We have to express x in terms of y. Whenever you see this instruction, express a variable in terms of other variables, all it means is to solve for that variable. So let's use our rules of exponents and a little bit of thinking here. If I have 5 to the b plus 1, well, somehow I added exponents. The exponents I added were 5 to the b and a 5 to the first, so that means I must have been multiplying those two things together. If I had multiplied those two, my answer would have been this. So all of that is equal to x. It says that 5 to the b is equal to y, so now we can replace 5 to the b with a y, and it says y times 5 is equal to x. My job was to express x in terms of y, so my answer is x is equal to 5y. Now x is expressed in terms of y. And this last one down here, again, now applying rules of exponents to come up with the solution we need here. And what is the value of a if 27 squared is 9 to the a? Well, we're looking for similar bases when we're working with our laws of exponents. Just like up here, we had to have similar bases. So let's think about how we can rewrite 27. I can rewrite 27 as 3 to the third power. All I did was change the 27. That means I still have that 2 exponent outside. And how can we rewrite 9? Well, I'll rewrite 9 as 3 squared. And again, we didn't change that exponent of a, so we'll have to bring it down. So now I have this expression that says 3 to the, well, 3 times 2 is 6, is equal to, well, 2 times a is 2a. The only way for this to be a true statement is if this number and this number are the same. So that gives rise to a little equation that I can write out. And the little equation says that 6 is equal to 2a. We'll divide both sides by 2. A is equal to 3. And you can go back and you can check that. If you raise 9 to the third power, you'll get the same thing as if you raise 27 to the second power.